Hello friends, welcome to my lecture on lattices. We define first lattice as an algebraic system. By an algebraic system, what do we mean by an algebraic system? By an algebraic system we mean a set together with a few rules for combining elements of the set to form other elements of the set. A non-empty set L together with two binary compositions join and meet, okay, is said to be a lattice if the following conditions are satisfied. So, this is the definition for lattice as an algebraic system. We consider two binary operations join and meet, okay. So, if a set contains these two binary compositions, it is closed with respect to these two binary compositions and satisfies the following properties, then it will be called lattice as an algebraic structure. So, commutative property for any AB belonging to L, A join B, A meet B equal to B meet A and A join B equal to B join A. So, commutative laws hold. Then associative property for ABC belonging to L, A meet B meet C equal to A meet B meet C and A join B join C equal to A join B join C. Okay. Then we have absorption properties. If you take any AB belonging to L, then A meet A join B equal to A and A join A meet B equal to A. So, if commutative properties, associative properties and absorption properties hold on a set L which is closed with respect to two compositions join and meet, we will call it as a lattice as an algebraic structure, and such a lattice is denoted by this notation. Now, there is a connection between the two definitions, lattice as a poset and lattice as an algebraic structure. The two definitions of lattice are equivalent. So, let us prove how the two definitions of lattice are equivalent. Let us first assume that L is a lattice as a poset. Okay. We are going to show that L is a lattice as poset if and only if L is a lattice as an algebraic structure. Okay. So, let us say let L be a lattice as poset, then A join B, as we know A join B is least upper bound of A B which is there in L, and A meet B equal to GLB of A B which is there in L. So, A join B and A meet B are two binary compositions in L. We are going to prove that L is a lattice as an algebraic structure. So, for that we need to show that A join B and A meet B are two binary compositions in L. So, that follows. Now, let us say the commutative laws, associative laws and absorption laws. When we considered the lattice as a poset, there we had shown that commutative laws, associative laws and absorption laws all hold true. So, L is a lattice as an algebra. Conversely, let L be a lattice as an algebra, then first we will prove that L is a poset. So, let us define a relation precedes on L such that A precedes B if and only if A meet B is equal to A. Now, we have to show that L is a lattice as L is a lattice as a poset. So, first we show that it is ordered, that is it is a partial order set. So, we show that this precedes relation in defined on L is reflexive. So, let us see how we prove that it is reflexive. In order to prove that L is reflexive, we have to show that A precedes A. Okay. A precedes A means we have to show that A precedes A means we have to show that A meet A equal to A. Okay. We have to show that A meet A equal to A. Now, what we do, take any L A belonging to L, then A meet A equal to A, because from this absorption law, okay, from the absorption laws hold, because L is a lattice as a poset. So, A meet A join B equal to A, absorption law 1 and absorption law 2, A join A meet B equal to A. Now, in one what you do, replace B by this B by A meet B. Okay. Then what we will have? A meet A join B are replacing B by A meet B. So, A meet B, okay, equal to A. And now let us use the second absorption law. A join A meet B equal to A. So, put that value here. Okay. Then we have A meet A equal to A, and A meet A equal to A by our definition implies A is precedes A. Okay. So, the operation this precedes is a reflexive operation. Now, anti-symmetry, let us say take any two A B belonging to L, then assume that A precedes B and B precedes A. Now, A precedes B means by our definition A meet B equal to A and B precedes A means B meet A equal to B. Okay. Now, A meet B equal to B meet A because of the commutative law. So, A meet B equal to B meet A, and therefore, A is equal to B, and so we say that this operation defined on L is symmetric. Now, let us show that it is transitive. Okay. So, take A less than or equal to B, assume A less than or equal to B, A precedes B and B precedes C. Okay. Then we have to show that A precedes C. Okay. So, in order to prove that A precedes C, from A precedes B, it follows that A meet B equal to A, and from B precedes C, it follows that B meet C equal to B. Then in order to prove that A precedes C, we have to show that A meet C equal to A. So, consider A meet C. Okay. Put the value of A here, A is equal to A meet B. So, A meet B meet C. Now, use the associative law. So, we can write it as A meet B meet C, B meet C equal to C. So, we get A meet B, okay, and A meet B is equal to A. So, we get A here. So, A meet C equal to A implies that A precedes C, and therefore, the relation precedes is a transitive relation on the set. Now, let us show that the greatest lower bound of A B exists and the least upper bound of A B exists, where A and B are any two elements in L. So, we will first show that GLB of A B is equal to A meet B, okay, and A meet B is there in the set L. So, GLB of A B will exist and it will belong to L. Now, let us so for this we will first show that A meet B is less than or equal to A, and A meet B is less than or equal to A meet B is precedes B. Okay. Now, proof of A meet B less than or equal to A. First we are proving this. Now, why we are proving A meet B less than or equal to A and A meet B less than or equal to B? Because we want to show that A meet B is a lower bound of A and B. Okay. So, A meet B precedes A because A meet B meet A. A meet B meet A is A meet B by commutative law can be written as B meet A, okay, meet A. So, this is again by associative law B meet A meet A, okay, and A meet A equal to A. So, we get B meet A, okay. B meet A is equal to A meet B. So, A meet B meet A equal to A meet B. This means that A meet B is less than precedes A, okay. A meet B precedes A. Now, similarly A meet B meet B, okay. Now, we are going to show that A meet B precedes B, okay. So, A meet B meet B equal to A meet B meet B. B meet B is equal to B. So, we get A meet B, okay, and thus A meet B is precedes B, okay. So, A meet B is a lower bound of A and B, okay. So, therefore, A meet B is a lower bound of A and B, okay. Now, we will show that if C is any other lower bound of A and B, then C precedes A meet B. So, that A meet B is the greatest lower bound of A and B. Now, let us say let C be any other lower bound of A and B, then C precedes A and C precedes B, okay. Now, C precedes A by our definition gives C meet A equal to C and C precedes B by our definition gives C meet B equal to C. We have to show that C precedes A meet B, so that A meet B becomes the greatest lower bound. Now, in order to show that C precedes A meet B, we have to show C meet A meet B equal to C. Okay. So, C meet A meet B equal to C we have to show. Okay. C meet A meet B equal to associative law gives C meet A meet B, okay, and C meet A equal to C. So, we get C. Okay. So, C meet A meet B equal to C, therefore, C precedes A meet B, and hence A meet B is the greatest lower bound of A and B. Now, we assumed that A precedes B if and only if A meet B equal to A. We shall show that this is also equivalent to A join B equal to B. If we can show that it is equal to A join B equal to B, then by using duality we shall be able to say that A join B is the greatest lower bound of is the least upper bound of A and B. Okay. So, we have to show that A meet B implies and implied by A join B equal to B. Okay. Now, let us first assume that A meet B equal to A. Okay. A meet B equal to A, and we want to show that A join B equal to B. So, then A join B becomes A meet B meet B. Okay. Okay, A meet B join B. Okay, A meet B join B becomes A join B. Now, B equal to, okay. So, from here what happens? Now A meet B join B. A meet B join B equal to B. Okay, A meet B, because A meet B join B is equal to B by absorption law. So, this is equal to B, and then this is A join B. Okay. So, A B equal to A join B. Now, let us consider A join B equal to B. Okay. A join B, let us prove the converse. A join B equal to B, then we have to show that A meet B equal to A. So, A meet B equal to A meet A join B. Okay. A join B, but again we use absorption law and this becomes A. Okay. So, supremum of, okay. So, what happens? A meet B equal to A if and only if A join B equal to B. Okay. And also A precedes B if and only if this. Okay. So, when we assume that A precedes B if and only if A meet B equal to A, okay, and it turned out that A meet B equal to greatest lower bound of A and B. Okay. By duality theory, it follows that A precedes B if and only if A join B equal to B will imply that A join B is the least upper bound of A and B. Okay. So, A join B, okay, A join B equal to B is the least upper bound, A join B is equal to is the least upper bound of A and B, and A join B equal to B means A join B implies A join B belongs to L, and A meet B equal to A means that A meet B belongs to L. Okay. So, further A meet B and A join B belong to L. Okay. So, L contains the greatest lower bound and the least upper bound. Okay. Hence, L is a lattice as a poset. So, this proves the theorem. Now, let us define sublattices. Let M be a non-empty subset of a lattice L, then M is called a sublattice of L if M itself is a lattice with respect to the operations of L. Okay. Note that M is a sublattice of L if and only if M is closed under the operations meet and join of L. Okay. So, that means if A and B are any two elements of M, okay, then M A meet B belong to M and A meet A join B belong to M. Okay. Thus, the supremum and infimum of any pair of elements in M must also be an element of M. So, let us now take an example. Consider the set of positive integers under the operation of divisibility. We know that it is a lattice. Okay. Let us consider its subset D12. D12 consists of 1, 2, 3, 4, then 6, then 12. They are all divisors of 12. Okay. So, let us draw Hesse diagram to show that D12 is a sublattice. Okay. So, 1, then 2, then we have 4, then we have 6. Okay. And 1 divides 3. So, we have 3, then we have 4 divides 12. So, this 3 divides 6 and 6 divides 12. Okay. So, from this Hesse diagram it follows that D12 is a sublattice. Now, let us consider a subset C of n, C equal to 2, 3, 6. Okay, 2, 3, 6. So, let us draw this diagram 2, then we have 6, then we have 3. Okay, then we have. Okay. So, from this Hesse diagram it follows that 2, 3, 6 is not a sublattice, okay, of n, because the infimum of 2, 3, infimum of 2, 3 is 1, infimum of 2, 3 means GCD of, under the operation of divisibility, infimum becomes GCD and the supremum becomes LCM. So, infimum of 2, 3 is equal to GCD of 2, 3 and GCD of 2, 3 is equal to 1. So, this means that 1, and since 1 does not belong to C, 1 does not belong to C, it follows that C is not a sublattice, because infimum of 2, 3, 2, 3, infimum of 2, 3 means 2 meet 3. 2 meet 3 is infimum of 2, 3. Okay. So, 2 meet 3 does not belong to C. Okay. So, C is not closed under the operation meet. Now, let us go to another example. Consider the lattice L shown in figure A below. Okay. Determine whether or not each of the following is a sublattice of L. Okay. So, let us take X A B by. Let us consider L1. Okay. If we take AB, okay, take AB here, then we can see that C is the least upper bound for the pair AB, X is the greatest lower bound. Okay. Since C is the least upper bound of AB, okay, and C does not belong to L1, we have, it follows that L1 is not a lattice. Now, if you take L2, L2 is equal to X A E Y. Okay. So, you take, say, X here, A here, okay, E is here, Y is here. Okay. You take any pair, say for example, you take A and E. Okay. For A and E, okay, X is the lower greatest lower bound, Y is the least upper bound, okay, and X and Y both belong to L2. If you take any other pair, say for example, you consider A and X, then X is the greatest lower bound, A is the least upper bound. Okay. If you consider A and Y, okay, let us consider A and Y. If we take A and Y, then the least upper bound is Y, which is there, and the greatest lower bound is A itself, because A precedes A precedes Y. So, A is the greatest lower bound. Okay. So, A greatest lower bound, A least upper bound of A by is equal to by, okay. So, A meet A join by, okay, and A meet by will be equal to infimum of A by. If you find the infimum of A y, infimum of A y will be A, okay. So, you take any two elements belonging to L2, okay, their infimum and supremum belong to L2. So, L2 is a lattice. Now, let us take A C D y, okay. A, this is A, C and then D and then y, okay. So, A C D y, here you take any pair, say you take A y for example, for A y, A is the least greatest lower bound, y is the least upper bound. If you take A and C, okay, then A and C, A is the greatest lower bound, C is the least upper bound. If you take say for example, you take C and D, okay, if you take C and D, then for C D the greatest lower bound will be, greatest lower bound is A, okay, and the least upper bound is y. Okay, so, you take any pair of points here in L2 which is L3 which is A C D y, we find that there are greatest lower bound and least upper bound exists. So, L3 is also a lattice. L3 now, let us take L4 x C D y. So, x here C D and y, okay. Now, for C D, if you take C D, for the pair C D, A is the greatest lower bound, okay. For C D, for C D, okay, A is the greatest lower bound, okay, and A does not belong to L4, okay. So, L4 is not a sublattice. Okay, so, L1 is not a sublattice and L4 is not a sublattice. The two other two, L2 and L3 are sublattices. Now, let us define bounded lattice. Let L be a lattice, then L is called to have a lower bound denoted by this 0 if for any element x in L we have 0 precedes x, okay. Analogously, L is said to have an upper bound denoted 1 if for any x in L we have x precedes 1, okay. We say that L is bounded if L has both a lower bound and an upper bound, okay. In such a lattice we have the identities A meet A join 1 equal to 1, A meet 1 equal to A join 0 equal to A meet 0 equal to 0. These elements denoted by 0 and by 1, they are the least and greatest elements of L, okay. So, 0 is the least element of L, and 1 is the greatest element of L. So, in other words, we say that if L is a lattice, then it is called bounded if it has least element as well as the greatest element. Least element is denoted by 0 and greatest element is denoted by 1. Let us show these identities. We have to show that A join 1 equal to 1, okay. So, to prove this A join 1 equal to 1, what we notice, since 1 is the greatest element, and A join 1 belongs to L, we have A join 1 precedes 1. Okay? A join 1 precedes 1. Now, A join 1 by definition, A join 1 is the LC supremum, least upper bound. Okay? Least upper bound, that is supremum of A n 1, A n 1. So, 1 precedes A join 1. Okay? 1 precedes A join 1. So, this this condition A join 1 precedes 1 and this other one 1 precedes A join 1, they together give us A join 1 equal to 1 by anti-symmetry. Okay. Similarly, one can show that A meet 1 is equal to A. Now, let us show that A join 0 equal to A. So, A join 0 equal to A, let us prove this. Okay. Since A join 0 is the supremum of A and 0, okay, we have 0 precedes A join 0. Okay. Now, we have to show that, we show that A join 0 precedes, here we have to write A. See, A join 0 equal to supremum of A and 0. So, A precedes A join 0. Now, let us show that A join 0 precedes A. Okay. So, we will have to show that A is an upper bound for A and 0, then A will succeed A join 0, because A join 0 is the least upper bound. Okay. So, we know so A is precedes A by reflexive property and 0 is the least element. So, 0 precedes A. Okay. And therefore, A is an upper bound for A and 0. So, this implies that A join 0 precedes A. Okay. Now, this condition condition and this condition together, they give you A join 0 equal to A by anti-symmetry, and similarly we can show A meet 0 equal to 0. So, if L is a bounded lattice, okay, then it has least and greatest element denoted by 0 and 1, and it satisfies these properties. Let us consider this example. Identify the lower and upper bounds if they exist of the set of positive integer and with the usual ordering. Now, n contains 1, 2, 3, 4 and so on, okay, and the ordering is given as usual ordering. Usual ordering means less than or equal to. Okay. With less than or equal to 1 is the least element, in n, and n does not have a greatest element. There is no element in n which succeeds every other element of n. Okay. Now, identify the lower and upper bounds if they exist of the set. This lower and upper bound means least and greatest elements. So, you can see 1 2 is an interval here, open interval, 1 2 is an open interval. So, it does not have the least element and it does not have the greatest element if it is ordered by usual order. Okay. So, in the second example, the least element and the greatest element do not belong to are not there. Okay. Least element and greatest element do not exist. Now, let us go to this example. Identify the lower and upper bounds, least and greatest element if they exist of the power set P A of a set A under the operation intersection and union. Okay. So, P A is the power set of A. Power set of A, okay, and intersection meet is the intersection operation. So, let C be subset of A and D be subset of A, okay. C D belong to P A, okay. So, we define intersection union means we define meet and join, join be divided as join be defined as C union D, okay, and meet be defined as C intersection D, okay. Now, if you take this P A, so P A contains all subsets of A, so phi is there, okay, also A is there. Phi is the least element, because phi is contained in every other element of P A. Phi is contained in say M for every M belonging to P A. Okay. So, it is the least element, okay, and A is the greatest element. Every subset of every set belonging to P A is a subset of A. Okay. Now, let us show that every finite lattice is bounded. Let us assume that L contains elements A 1, A 2 and so on A n. L contains finite number of elements, let us say that it contains n elements A 1, A 2, A n, we want, so it is a finite lattice, we want to prove that it is bounded, that means it has least element as well as the greatest element. Let us define B 1 equal to A 1, B 2 equal to A 2, meet B 1, B 3 equal to A 3 meet B 2 and so on, B n equal to A n meet B n minus 1. Okay. Then what do we notice? Okay. B 2 is equal to A 2 meet B 1. So, B 2 is the greatest lower bound of A 2 and B 1. So, B 2 precedes B 1, B 3 precedes B 2 and so on, B n precedes B n minus 1. Okay. So, we can see B n precedes B n minus 1, B n minus 1 precedes B n minus 2 and so on. So, we get B n precedes B n minus 1, B n minus 1 precedes B n minus 2 and so on precedes B 1, B 1 means A 1. In this process you can see that B n precedes A I for every I equal to 1, 2 and so on up to n, because from here you can see B n equal to A n meet B n minus 1. So, B n is the greatest lower bound of A n and B n minus 1. So, B n precedes A n and B n precedes B n minus 1. Now, B n precedes A n, okay, and then from the previous equation B n minus 1 precedes A n minus 1, but B n precedes A n and A n precedes and B n precedes we can say if you want to prove that B n precedes A I for every I. So, then from B n precedes B n equal to A n meet B n minus 1. It follows that B n precedes A n. Okay. B n minus 1 equal to A n minus 1 meet B n minus 2. Okay. So, B n minus 1 precedes A n minus 2. Okay. Now, B n precedes B n minus 1 and Bn minus 1 precedes An minus 2. So, by antisymmetry Bn precedes An minus 2. Continuing this process, we can show that Bn precedes An minus 3 and so on, and then it follows that Bn precedes Ai for every I. Okay. So, Bn is the greatest least element of, hence Bn is the least element of A1, A2, An, and Bn is equal to An, Bn minus 1, Bn minus 1 is equal to Bn minus 2, meet Bn minus 2. So, what we get? Bn becomes A1 meet A2 meet A3 and so on meet An. Okay. Now, clearly L is a lattice. So, A1 meet A2 meet A3 and so on meet An is an element of L by associativity. So, this is an element of L. So, L has the least element. Okay. Similarly, we can show that L has the greatest element. And the greatest element is A1 join A2 join A3 and so on join An. So, when L is a finite lattice, it is always bounded because it contains the least element and the greatest element. So, that is all in this lecture. Thank you very much for your attention.